All right, in this lesson today, we're going to be exploring all different types of things related to energy. We'll be looking at kinetic energy, potential energy, different types, the work energy theorem, as well as we'll be exploring the conservation of mechanical energy. So we'll begin by giving a definition of energy. So energy is defined as the ability to do work. It seems like a circular definition because, of course, work is defined as a transfer of energy into or out of a system. Nevertheless, the basic definition of energy is the ability to do work. There's two main flavors of energy, two main types. You can divide them into two groups. The first group would be kinetic energy, which we abbreviate KE, and potential energy, which we would abbreviate PE. And there's different types of potential energy. There's gravitational, there is elastic. We'll be exploring electric potential energy. And you might have, in chemistry, learned about chemical potential energy, specifically the energy that's stored in bonds. But in physics, we'll be looking at these three here. Okay. I'm not going to fill that in now, just the different types, so we'll just do that. Simply defined then, kinetic energy is the energy of motion. Kinetic means moving, so it is the energy of motion. There are four main types of kinetic energy. The first type is sound energy. So that's associated with sound waves. Next is thermal energy. It's also known as heat. Electric energy is the energy that's associated with moving charges. And radiant energy is electromagnetic energy that radiates from a source. How does an object obtain kinetic energy? It must have a measurable velocity. So if an object is going to move, then of course dynamics tells us that an unbalanced force, MA, which is our F net, must be applied to the object. Now normally in class we would take time to develop a formula for kinetic energy. Due to this remote learning situation, I'm just going to give you the formula. I would not require you to derive it, it's not necessary. If you are interested in the derivation in the formula, then you can refer to your textbook. So kinetic energy, KE, is equal to 1/2 times the mass times the square of the velocity. So KE equals 1/2 mv squared, and the unit is the joule. So energy is always measured in joules. Okay. I guess before we move on, it is necessary to note that the kinetic energy is directly proportional to the mass. It's also worth noting that the kinetic energy is directly proportional to the square of the speed. So if you double the mass, you double the KE. However, if you double your speed, then you actually increase the KE by a factor of 4. And that's why moving objects, as they move faster, okay, they can be more dangerous. So if you're thinking about safe driving, a car that's moving at 40 kilometers an hour has 4 times the amount of kinetic energy as an object moving 20 kilometers an hour. And that's why collisions, okay, are much more devastating the faster you go. So it's worth noting that as you increase your speed, you increase your velocity by the square of the speed. Sorry, if I say velocity, you increase your kinetic energy by the square of the speed. Okay, we'll get into some examples with the kinetic energy equation later, but we're going to jump right into the work energy theorem. So remember that work is defined as a transfer of energy. Work is done when an unbalanced force acts over a distance. And so therefore, if an object is going to start to move, i.e. if it's going to gain kinetic energy, then work must be done on an object. Think about it. If you've got the ground and you've got a soccer ball, if B is 0, it's at rest. The only way to get it to move, B greater than 0, is to apply an F net over a delta D. Therefore, work is done. You do work on the ball, you get it to move. And the energy then that the ball has now, it would be the energy of movement, which is kinetic energy in the moving ball. And the ball at rest has 0 kinetic energy. Okay, so what does this bring us to? It brings us to the work energy theorem, which states that simply work is equal to a change in energy. If you do work on an object, it's going to change its energy level. So if we expand that, change in anything is equal to the final energy level or final amount minus the initial. So work would equal the final energy level minus the initial energy level, whatever it is, and we could expand work to be F delta D equals the change in energy. So that would be worth noting. Okay, the expanded version of the work energy theorem. Okay, moving on. We can calculate the kinetic energy of an object very simply using the formula Ke equals 1/2 mv squared. So we read the question, we have a hockey puck, we have its mass, and it's moving with a velocity of 95 kilometers per hour, and there's the V. What's the kinetic energy of the hockey puck? Well, the kinetic energy equals 1/2 mv squared. M must be in kilograms, and V must be in meters per second. So if you want to pause the video right now, you can try on your own to calculate the kinetic energy of the hockey puck. And I'll give you the answer in a second. Okay, so to plug this in, the kinetic energy is 1/2 mv squared, and we just have to make sure we do our conversion. So the mass is in kilograms, so we have to divide by 1,000. So that would be 1/2 times 350 over 1,000 squared times, whoops, not squared, that's m times v squared. The v is 95 kilometers per hour. We divide that by 3.6, get it to meters per second. And we would square that, and we would get our answer. So we would go 350 divided by 1,000 times 95 divided by 3.6 squared, and you would get 243.73 joules. The sig figs would be 240 joules. So where did that energy come from? Where did this kinetic energy come from? It came from the force that was applied by the hockey stick over the distance while it was in contact to get the puck moving. And as the puck is moving, it has 240 joules of kinetic energy. We can use kinetic energy to find velocity if we want. Again, Ke equals 1/2 mv squared. We can easily solve for v by isolating it. And if we're talking about calculating the final velocity v2, then we are going to use the word change in energy theorem. So a cue ball in pool is shot towards the left corner pocket during a game of 9-ball pool. The cue ball has a mass of 170 grams, and it has 19.71 joules of kinetic energy. How fast is the cue ball moving towards the corner pocket? So here, I don't know why we said final velocity. We're assuming it's already moving and there's no change. So we will just use the formula KE equals 1/2 mv squared. Now, if we're going to isolate it, I'll go through the algebra and then you can just have that formula down. Or you can just substitute in KE and M and then move it down. So we want to isolate V, so we will multiply by 2 and divide by M. So 2KE divided by M equals V squared. So if we want V, we would square root both sides. So solving for V, we get the square root out of 2KE divided by M. So that would be worth putting on the formula sheet, okay? Or you can just use this formula and plug in KE and M. Okay, so we know KE and we know M, so we can easily solve for the velocity of the cue ball. So the velocity of the cue ball will equal the square root of 2 times 19.1 joules of energy divided by M. And so the mass was in grams, 170 grams, so convert that, divide by 1,000, 0.170 kilograms, and we can isolate velocity. So 2 times 19.1 divided by 0.17, and then we will take the square root, and you get 14.99 meters per second. And we want 2 sig figs, so the velocity of the ball would equal 15 meters per second. That would be its velocity, so we need a direction, vector, and positive towards the corner pocket. Okay, so a basic example of the work change in energy theorem. Again, work done causes energy to change. A marathon runner has a mass 65 kilograms. It runs at 12.1 kilometers per hour. How much energy does the marathon runner have? So this is just solving for KE. If you want to pause the video, you can solve it on your own. Okay, so it's 1/2 mv squared, 1/2 times 65 times 12.1 divided by 3.6 for the conversion to meters per second squared. So we take 65 times 12.1 divided by 3.6 squared, and you get 734 joules. That would be the initial KEI. That would be the initial kinetic energy. During the final 150 meters of the marathon, the runner decides to go all out and sprint to the finish line. How much work is required for the runner to increase his speed to 19.3 kilometers per hour? Where does this energy come from? So work equals change in energy. Specifically, we're talking about kinetic energy, so it would be the final kinetic energy minus the initial kinetic energy. So we have to calculate the final kinetic energy using the formula. So we'll solve it over here. KEF final equals 1/2 times 65 kilograms times 19.3 over 3.6 for the conversion squared. So we'll find that value. So 65 times 19.3 kilometers per hour divided by 3.6 for the conversion squared. And you get 1,868 joules. So that's the final kinetic energy. So to get the work done, we would take that value, 1,868 joules, minus the initial value. The initial kinetic energy was 734 joules. And you can easily figure that out. 1868 minus 734, we get 1,134 joules. That's the amount of work done to increase the speed of the gun. Where does this energy come from? The energy comes from the stored chemical potential energy in the cells of the muscle of the runner. That's essentially where it would come from. And that is the basic example of the work change in energy theorem. Okay, moving on to gravitational potential energy. Gravitational potential energy refers to the amount of energy that's stored in a gravitational field. We know that if you lift something up, you have to do work against the force of gravity, because the force of gravity is always pulling down. Okay. So, if we look at a free body diagram, we know that Fg is always down. And if you want to move an object upwards, you have to lift it. So we'll call this a lifting force. Now, if we've got an object on the ground, so there's the ground, and the height of the ground, h1, is 0 meters. We've got an object here, and we're going to lift it up. It's going to be at a new height, h2. Now, obviously, h2 is going to be greater than 0 meters, because it's above the ground. So essentially, then, by lifting the object from the ground to a height, we move the delta d. The delta d would be h2 minus h1, and if h1 is 0, the delta d would equal the height above the ground. Or we could simply just call it height. Now, the work that we have to do to lift this object would equal the lift force multiplied by delta d, F delta d. Now, the basic amount of force needed to lift the object would equal the force of gravity, which is equal to mg, and the delta d would be the height, which would be h. And that's the work done to lift an object up. So, it turns out that that amount of work that we do to lift the object up is equal to the gravitational potential energy. So, potential energy, and we call that PEG, gravitational, equals mass times g, that's on Earth 9.8 times h. And that would be the formula for gravitational potential energy. If we lift to different, if we lift to even more different heights, we can get a relative gravitational potential energy, which relates to the work change in, which is equals to the work change in energy theorem. So if the PEG, that's just potential energy gravitational, would equal mgh. And so if we're going to be lifting objects at different heights, the change in equal F minus PEI, which would be mgh2 minus mgh1, which we could then factor out mg times h2 final height minus initial height, H1. So that might become useful for us in certain situations. Okay, calculating the gravitational potential energy. So we have a circus duck with a mass, and it is launched into the air from the ground, and we want to know how much potential energy that duck will gain. So assuming from the ground H1 equals 0, potential energy, gravitational potential energy equals mgh. So you can pause now and try it on your own. Okay, so now we would just take 3.8 times 9.8, because g on Earth always equals 9.8, and times by the height, 125 meters. We get 4,655 joules. 2 sig figs, 4,600 joules. Gravitational potential energy. Okay. Calculating relative gravitational energy. A watermelon mass 2.5 kilograms rolls off a countertop that's 1.2 meters high onto the lap of a person that's 0.65 meters above the floor. What is the gravitational potential energy on the counter and on the lap of the surprised person? So on the counter, gravitational potential energy is simply mgh, which is 2.5 kilograms times 9.8 times 1.2 meters. 5 times 9.8 times 1.2. And you get 29.4 joules. How about on the lap of the surprised person? It's simply DEG equals mgh. So we've got 2.5 times 9.8, and the person is 65 centimeters above the ground, 0.65 meters. You get 15.9 or 15.9 joules. So you can see that the energy is less on the person lap versus the counter because it's closer to the ground. How much work was done by gravity when the watermelon rolled from the table to the lap of the person? So the work done will equal the change in energy, which is the final minus the initial. In this case, we're talking potential energy. So the final was 15.9 joules minus the initial gravitational energy, which was 29.4 joules. So 15.9 minus 29.4 gives us negative 13.5 joules. Why was the energy negative? It's a negative energy change because energy was released from the system. That energy that was stored in the gravitational field became kinetic energy as it was falling from the counter to the lap of the person. So that watermelon lost 13.5 joules of potential energy. So if we want to know how much work is done by gravity when it rolls from the lap of the person to the ground, then it would be negative 15.9 joules, because on the bottom, on the ground, it would have 0 joules. Okay, the next type of potential energy is energy that's stored in a spring or stretching a rope. Stretching a elastic band or something that's compressible. And we call this elastic potential energy. So it's potential energy, and we'll use S for spring for elastic. To determine the value, you know how you have to figure out how much energy is needed to force or work is needed to stretch or compress a spring through displacement X. So X is the amount of displacement of stretching or compressing a spring. There are springs that stretch and compress easily and others that do not. And so it can be shown experimentally that the amount of displacement of an elastic object is directly proportional to the amount of force used to deform it. And we get Hooke's law, which is F equals kx, and k is what we call a spring constant. So a spring that's in your bed would have a smaller spring constant than, let's say, a spring that is in the shock of a car to absorb energy. So larger spring constant means the spring is stiffer, it requires a lot more force to deform it, and a smaller constant means that the spring does not require as much work to move that, to stretch or to compress that object. Okay, so we have here a visual of Hooke's law. We have the stretching force F, and we have the extension X. And so you can see that it's a linear relationship. Eventually there becomes a curve. That's what we call the elastic limit. Eventually, I'm sure you've noticed, like with a slinky or something, if you stretch it too much, it doesn't go back to normal. So there's always going to be this elastic limit. So within the elastic limit, it's linear, and the slope would represent K. So K is a constant. Stretching and compressing a spring, the force varies linearly. Therefore, the average force to stretch or compress it at distance x would be 1/2 times kx. That would be the average force. So now if we take that average force and the amount of work done, if we know that work equals F delta D, and delta D in this case equals X, the work done would equal the average force, 1/2 F times Kx, multiplied by X, gives us the formula 1/2 Kx squared, which essentially is the amount of work that's done to stretch or compress the spring. That energy is stored or released from the spring, which we call elastic potential energy. So the amount of elastic potential energy equals 1/2 times Kx squared. And that would be another important formula. So we've covered off kinetic energy, gravitational energy, and elastic energy. Okay. I think I just defined it, so working ahead. Yeah, so we've defined it. Again, I'll write it one more time. So elastic potential energy, PES, equals 1/2 Ax squared. X must be in meters, okay? And K must be in newtons per meter. So it's very important that those units are as is. As you can see, newtons per meter for K, and X is in meters. Okay, an example of this. 1,550 kilogram car, mass of the car, is on a metal plate that's supported by a coiled spring. The spring constant is 70,000 newtons per meter. How much is the spring compressed? How much is the spring compressed? That's solving for X. So you've got a plate, you've got a car that's sitting on it, and there is a force pushing down, and there is a spring that is going to be compressed by a distance x. So what force is pushing down on the string? It would be Fg, so that's mg. And the force that's pushing back would be the average force, and that's 1/2 kx. So we can use this relationship. How much is the spring compressed beyond its normal length? So that once it gets compressed, F net is 0. So the average force of the spring would equal Fg. So 1/2 kx would equal mg. And now we've got the ability to solve for x. You can try and pause the video right now and solve it on your own. Okay, and we'll go through it then. So I'm going to isolate x, so I'm going to multiply by 2 and divide by k. So x would equal 2mg divided by k. So 2 times 1550 times 9.8, g again on Earth is 9.8, divided by the k, and I believe the k was 70,000. You can isolate the amount that the spring is compressed. So 2 times 1550 times 9.8, and then divided by 70,000, and you get 0.434. 0.434 meters, which would be about 43 centimeters. So the 2 sig figs, x would equal 0.43 meters. Okay. How much energy is stored in the spring? That is the elastic potential energy. So the elastic potential energy is equal to 1/2 times kx squared. We know k, and we just calculated x. You can try solving on your own. And it goes like this: 1/2 times 70,000 times 0.434 squared. Pretty straightforward calculation, but we can get the amount of energy that's stored. So 0.5 times 70,000 times 0.434 squared, and you get 6,592 joules. And I believe we have to take it we'll leave it at that. So 6,592 joules. We do have to round to 1 sig fig, so that'll be 6,000 joules. Again, you can see when you have to go to the least number of sig figs, it really changes the value. But that would be the amount of energy that's stored, and it would be a plus because, of course, the spring has been compressed. Okay, so this takes us to the last part of this lesson, which is the conservation of energy. So like conservation of momentum, energy is also conserved. So the system is a section of the universe. It's closed. No energy or matter can enter or leave. And this line of thinking is important to understand the LCE. LCE is an abbreviation for the law of conservation of energy. And so it's probably one of the most famous laws. And it's stated as follows. Number 1, you can't create or destroy energy. You can transfer it from one form to another without any loss. Number 2, the total energy of the universe always remains the same. And the energy can change form from one to another, but the total amount of energy always remains the same as long as the system being considered is closed, meaning no external force, i.e. no friction. Okay. So the work energy theorem fits nicely into the LCE. Example 1, consider a moving car braking suddenly and coming to a complete stop. How is the total energy of the system unchanged? So you can think about that. The second example you can think about is dropping a tennis ball above the ground. It falls to the ground, it bounces a number of times before it comes to a stop. You can think about how the energy changes and the total energy of the system remains unchanged. Okay, so the conservation of mechanical energy is stated as this. The total energy initially equals the total energy after an event. And so we have this little apostrophe, and it's called the prime marker, which means final. So for example, if we had, instead of saying V1 and V2, or V initial and V final, we could say V for initial and then V prime for final. So this is just something that you'll see in textbooks. So the prime is just really, it looks like a little apostrophe or really like a little tick mark in the exponent position. So this is the initial amount of energy, and this means the final. And it's basically stating that they have to be the same. So the total amount of energy in the system initially equals the total amount of energy in the system after an event has occurred. And how do we define the total amount of energy? Well, there are the two types. It's considered the sum total of the kinetic energy plus the potential energy. And of course, we have two types of potential energy, gravitational and elastic in these examples. So really, if we expanded it out, the total amount of energy would equal kinetic energy plus gravitational potential energy plus elastic potential energy. Now, if an object doesn't have a certain amount of energy, then it's just zero and we don't include it. So it's not too difficult. Again, we know that kinetic energy equals 1/2 mv squared. Gravitational potential energy equals mgh. And elastic potential energy equals 1/2 kx squared. So if we wanted an expression for the sum total of energy, it would equal 1/2 mv squared plus mgh plus 1/2 kx squared. Now, you don't have to write that all out, but that would be the expanded version of the sum total of mechanical energy. So what we're basically saying then is that the sum total of the energy initially, E total, must equal, after some change has occurred, the E total prime. So the amount of energy before total equals the energy after. And if it's not true, then some outside agent like friction did work to take energy in or out. And friction, of course, generates heat, which is thermal energy, which takes energy away from the system in the form of heat, but it keeps the total amount of energy in the universe the same. So we can apply then the conservation of mechanical energy for different situations. So we have a parachutist has a mass, jumps out of a plane that's traveling at a certain speed, at a certain altitude h, above level ground. If we neglect air friction, you're going to then find the velocity of the object, of the parachutist after falling. Okay, now we're going to assume then that this V is irrelevant because it's horizontal only. to make our life a bit easier, we're just going to assume then that the vertical velocity would be 0. So the E total would then equal KE plus PEG plus PES. Now, we're going to say that there is no vertical velocity, so no kinetic energy. There is no spring involved, so the total energy of the parachutist initially is equal to its gravitational potential energy, which is equal to mgh, which we can find 80 kilograms times 9.8 times 3250 meters. So 80 times 9.8 times 3250, you get 2,548,000. 2,548,000 joules. Okay, so now this parachutist is at initial height, H1, and it falls to a secondary height, H2. Now we don't know what that is, but we do know that it fell 1,500 meters. And H1 was 3,250. So all we have to do is subtract the 1,500 from the 3,250, and H2, final height of the parachutist in this case would be 1,750 meters. Okay, we do know that as the parachutist falls, it's going to gain vertical velocity. So E total prime then would equal the final kinetic energy plus the final gravitational potential energy, because of course it's still above the ground. So now what we're saying is that E total equals E total prime. So we calculated it as 2,548,000 joules equals 1/2 mv squared plus mgh. So what we can do is calculate the final gravitational energy, subtract it, and then isolate V. So 2,548,000 equals 1/2 times 80 kilograms times V squared plus 80 times 9.8 meters, 9.8 for gravity times 1750. Okay, so all I'm going to do to save time is I'm going to subtract that from 2,548,000. I'm going to subtract and put in brackets 80 times 9.8 times 1750. And you get 1,176,000 joules. So 1,176,000 equals 1/2 times 80 times V squared. So 1/2 times 80, so that would be 40 times V squared. So now we can isolate V, divide by 40, and square roots. So V would equal the total divided by 40. And then you would take the square root of that, and you would get 171 meters per second. Now that's assuming no friction. That's not realistic. In real life, there is air resistance. There's no way you'd reach that speed, but for the context of this scenario, we use the conservation of energy to find the final velocity. So the second option is, what is the speed just before the parachutist hits the ground? So E total, you still know, at the beginning is 2,548,000 joules. You want to find your E total prime. Well, E total prime will equal KE prime plus PEG prime plus PES prime. Well, right before he hits the ground, H is 0, so there's going to be no gravitational energy, and there's going to be no elastic energy. So really, the only energy is in the form of kinetic energy. So E total equals E total prime, 2,548,000 joules equals KE prime, which allows you to solve for 1/2 mv squared, so you can isolate D. So I will let you try that on your own. You should get a V final speed of 252 meters per second. You can try calculating that on your own. I believe that takes us to the end of this lesson. So we covered off quite a bit, but that's pretty much the rest of the energy units. I put together a practice workbook for you, 3 question sets. 1 question set for work and energy, second question set for, the first question set is for work, energy, and kinetic energy. Second question set brings in potential energy, and the third question set brings in the law of conservation of energy. The plan is that you work on this today after the lesson, and I'm going to be assigning that for Monday. So there's going to be no formal lesson on Monday. Monday is going to be considered a work period for those work questions, but I will be uploading a concept check for this, as well as the unit assessment. That you will have until Friday, May 1st, to hand in the unit assessment. And I wish you the best of luck working with energy, calculating kinetic energy, potential energy, and the law of conservation of energy.